The TLDR is that you shouldn't be using raw pixels to train visuomotor policies. Instead, you should be using mid-level representations for this purpose. Hi, I'm Sasha Sachs, and I'll be presenting the results of our study, where we evaluate mid-level representations for both manipulation and navigation tasks. Mid-level representations are a processed encoding of raw sensor input that exhibits various invariances that might be useful for other downstream tasks. We examine representations driven by traditional computer vision objectives, and our studied set contains objectives from different common computer vision families, such as geometric, semantic, and texture-based tasks. We used representations from neural networks that were trained offline for different computer vision objectives, and the encoders produce image codes that contain the invariances learned over the course of that initial training. For example, if the feature encoder was trained for surface normals, then the latent features can be decoded into a surface normal image that preserves geometry while dropping color and texture. We test these mid-level representations as a drop-in replacement for pixels when training policies using RL, so that during RL training, the agents are provided only with the encoding phi of x and not the original image. We find that incorporating invariances in this way improves both generalization and training speed when compared to learning from scratch or using other invariance learning techniques, such as domain randomization. Specifically, we test three main hypotheses. First, does using mid-level representations simplify training to the point where you can use these to train for more complex tasks than would otherwise be possible? 2, do the invariances improve generalization? And 3, how do using mid-level representations compare to using other forms of invariance learning, such as domain randomization? We find that these representations are surprisingly effective across a range of manipulation and navigation tasks. For hypothesis 1, we found that using mid-level representations, we could train agents to solve more difficult tasks than was possible otherwise. In fact, no matter how long we train the pixel-based agents, they often fail to learn anything at all. And this can be quantified pretty easily. Over 3 different manipulation tasks, with more difficult tasks shown here on the right, agents trained using mid-level features are indicated by hatched bars, and taller bars indicate better performance. Translucent bars show training performance, and opaque bars show performance on a held-out test set. You can see that on the hardest task, agents trained directly from pixels fail to learn anything at all, even in the training environment. But how do these two stack up in the test environment? We tested all the policies in novel environments unseen during training. Agents using mid-level vision generalized significantly better than those trained from pixels. The mid-level agents are robust to minor distribution shifts, such as color, and they also generalized to unseen objects. In fact, they're generalized even better than agents trained from the true environment state. The true state, as it represents increasingly complex objects, becomes difficult to use. Agents using mid-level representations also generalized from simulation to real-world contexts. We tested this by training agents in the Gibson simulator to navigate to target points, and then applied these policies on a real Turtlebot 2 in a new space where the agent had no prior knowledge of it and no period for adaptation. Here you can see an example episode of an agent trained using mid-level features, gracefully navigating through a cluttered environment to a target coordinate that's around the corner in the far side of the frame. Agents using mid-level features significantly outperformed agents trained from scratch, and those agents trained from scratch didn't even outperform blind agents that had no camera on board at all. We tested this in multiple buildings, and complete statistics of all the episodes are available on our project website. In addition, egocentric dashboard videos from each episode is also available. So how does using mid-level representations compare to other invariance learning approaches? Well, compared to other techniques such as domain randomization, agents using mid-level representations can learn to solve more difficult tasks. This is because for domain randomization, learning becomes increasingly difficult as more axes of randomization are varied during training, a finding echoed in other works. Even for simple tasks, learning from scratch on domain randomized training environments can cause learning to collapse when different axes are randomized. Agents using mid-level vision can handle domain randomization during training. But even without this domain randomization, agents using the mid-level representations still develop the desired invariances. We can quantify this and conclude that domain randomization can improve robustness to domain shift, but mid-level representations do this and also simplify learning. In conclusion, we argue that mid-level representations should be the default inputs for training in RL, because they provide a scalable way to incorporate invariances. For more, check out our project website. Thanks for listening.